Alright, so continuing lecture 15, let's talk about the normal curvature. Start with a lemma. If alpha is a curve in M, then the acceleration dot the unit normal to the surface is equal to the shape operator acting on the velocity dot the velocity. Now, the proof of this, it's important to notice that this is not just u anywhere, this is u as a function of time in order to differentiate it. So in particular, u evaluated along the curve alpha of t is what's meant by this equation, right? So if you differentiate that, then the product rule gives you the acceleration dot the unit normal, again along the curve, dotted with the velocity, and then the derivative of the composed unit normal with curve. Now that is, of course, the covariant derivative. That's actually the covariant derivative of u in the alpha prime direction, which then is negative of that, of course, is being the shape operator. So there you go, there you have it. The normal component to the acceleration is given in terms of the shape operator like that. So this brings us to define the so-called normal curvature. So if we have a unit tangent to M, then k of u is equal to the shape operator of u dot u. This is the so-called normal curvature of M in the u direction at P. Some quick observations. The normal curvature of u is equal to the normal curvature of minus u. Alright, nothing too surprising there. If you put in minus u here, you pull out a minus, and then minus minus gives you plus. Now, the terminology normal curvature, at the moment it's a little bit mysterious, but that's explained by observations 2 and 3. If we take a unit speed curve, then the Frenet normal times the curvature at 0 is equal to the acceleration at 0. That's the Frenet-Sorey equations. So the curvature, the normal curvature then, is given by the Frenet curvature times the normal dotted with the unit normal to the surface, the normal to the curve, Frenet normal, unit normal to the surface, two different normals. Anyway, so to get rid of this pesky cosine theta term, we can insist that we're looking at a curve which takes either plus or minus u as its Frenet normal. In other words, we look at a so-called cross-section of the surface, well, section, the curve formed by the intersection of a, let's say, vertical plane, a plane which contains the unit normal, and the tangent vector u of interest. And the curve of intersection is denoted by sigma, and so by construction, n of 0 is going to be plus or minus the unit normal. Now, I have a little more written about this. So here's a picture of that. Again, so here's your surface M, and there's that vertical cross section. So in this vertical cross section, you have that intersecting curve, which we denote sigma. We assume sigma is unit speed. Mostly just so we have this times that without an extra speed factor floating around. And in that case, this dot product is plus or minus 1 because either the normal is u or the normal's anti-parallel to u. So the dot product is plus or minus 1, so the normal curvature is just plus or minus the Frenet curvature of the curve of intersection, the sigma. Now, I think the example of the saddle surface is very nice. You can look at these 4 different intersecting planes, like this right here would be like these 4 different cases for the saddle surface. In particular, these are the curves we studied before. We calculated the shape operator. Remember, before we calculated S of E1 was E2 and S of E2 was E1. And so the curve of intersection with the saddle surface and the, let's see here, this with E2, this is the y-axis, so this is like the x equals 0, z equals 0 plane, for what it's worth. This plane is y equals 0, z equals 0. Oh, z equals 0. Well, not z equals 0, it's just y equals 0. Excuse me, it's just x equals 0 plane, and this is the y equals 0 plane. X equals 0 and z equals 0 is the purple line. Y equals 0 and x equals 0 is that purple line. Of course, as you can see, the unit normal does not change along those lines. So the covariant derivative in both of these cases is 0. And likewise, the normal curvatures in the E1 direction and E2 direction, both 0. In contrast, if you look at those special curves on the saddle surface, right? Let's see if I can be so foolish as to try to draw it again. Let's see here. Uh-oh, I bet I forgot how to draw it already. Well, something like... Oh, I think I've forgotten how to draw it. Oh well, it was it was going better before. Oh well, you win some, you lose some. There's that curve, and then the other curve like this one, right? Horrible. Oh well, I tried. Anyway, those curves of intersection would appear as these purple curves here. Like this would be the blue one, and it will be the red one. Sadly, it's the intersection with the y equals x and y equals minus x planes. For the one, the surface bends up towards the unit normal. For the y equals minus x plane, the curve of intersection, the sigma, it bends. You can see the surface bending away from the unit normal at the point P we're studying, which is here. Right. So you have all these different things going on for the normal curvatures. You can see that as you let u sweep around in a full circle of directions, you get pretty much a full description of how the surface is bending, either towards the unit normal or away or both at a given point. In particular, though, if you think about it, I mean, for what it's worth, k is a function from unit vectors in the tangent space to the reals. It's a real valued function from a compact domain, whatever that means. But it is known from basic theorem of analysis that it must attain a maximum and minimum value. And those maximum and minimum values are known as the principal curvatures. And the directions, or more specifically the principal vectors for which k1 and k2 are attained, those are called the principal vectors. So for example, the cylinder has the rulings is one, the vectors along that are point in the direction of the unit of the ruling, like that. If we fix that point P, then E1 is a principal vector and E2 is a principal vector. K of E1 is 0. That's the maximum value. K of E2 is minus 1 over r. That's the minimum value for the normal curvature to the cylinder. In contrast, the sphere, or here's or almost a sphere. So if you pick any particular point, right, it doesn't matter what sort of sigma you look at. Sigmas are great circles for this one, right? Those curves of intersection. They're all circles, right? And those circles have curvature 1 over r, but the normal curvature is minus 1 over r because it is measured with respect to the outward normal, whereas the Frenet normal calculates the curvature with respect to the Frenet normal, which goes in, right? So, but the minus here is part of the definition. It's a consequence of the definition that we chose. And I suppose if you, well, let's see here, I'm trying to think. What was our definition? I've forgotten it already. What was K of U defined to be? I'm an idiot. Defined it like 3 seconds ago. Here it was. K of U is S of U dot U, right? And the shape operator was defined to be the covariant derivative in the U direction of the unit normal, big U, right? So if I was to say swap, if I was to exchange the unit normal for minus the unit normal, then the shape operator changes by a minus sign, right? And consequently, I think then the principal curvature would also change by a minus sign. Yeah. Well, something seems... Well, anyway, let's go on. We'll get back to that shortly. All right, so principal directions, principal curvatures. Sphere is very special because the minimum and maximum value for the normal curvature is the same. And in fact, every direction is principal. So such a case is called an umbilic point. In an umbilic point, it means the normal curvature is constant, and for all unit vectors at the point. So this brings us to our deeper discussion I promised you of the linear algebra of the shape operator. So let's get to that. In particular, I'm going to just go ahead and see right there, 9. So we went through that little calculation at the start of this part about differentiating the velocity dot u along along the curve alpha of t, and a little bit later in section 5.4, O'Neill shares with us a different calculation. I'm just going to go ahead and throw that in here because I feel like it's relevant. He tells us, he says, okay, well, we also have that u dot x, let's see here, xu is equal to 0. So here we're looking at x, say from d to m, a patch. I'm just thinking of m being simple for a second here. I mean, you can do this locally otherwise. And u, of course, the unit normal. To m, which I'm taking to be x of d for the moment. Anyway, of course, the unit normal dot this velocity, this coordinate partial velocity, as he called it earlier, it's got to be 0 because xu is in the xu is for a particular u naught v naught. That's an element of the tangent space at x of u naught. So annoying. V naught m, right? And so great, but this we can look at as a function of let's see here of v in particular, and that means we can say 0 is equal to the partial derivative with respect to v of u dot excuse me x sub u, partial velocity, right? And then product rule gives me what? It gives me partial u partial v, or u sub v if you like, dot xu plus u dot xuv with the obvious meaning, right? But what is u? What is this, right? Well, this is the derivative of the unit normal, right, along the v coordinate curve, right? So in other words, this, if you think about it for a bit, is really just minus s of xv, right? So what we have is minus s of xv dot xu is equal to oopsie, I seem to have put equality. I guess that means I move that to the other side, right? Minus u dot x of uv, or let's see here, let me clean this up a bit. S of xv dot xu is equal to the unit normal dot x of uv. All right. Now, of course, what does that mean? Well, we can go through the same argument with starting with like u dot xv being equal to 0 and looking at it as a function of u, taking the partial derivative with respect to u, doing the product rule, making the identification that the derivative of the unit normal along the coordinate curve is, well, that's exactly the shape operator acting on the partial velocity And so likewise, we can show that S of x u dot xv is equal to u dot x of vu. All right, but these are actually second derivatives with respect to the, the Cartesian coordinates u and v. And as we know from advanced calculus, if you do partial differentiation in two different orders, they match up for nice enough functions. Certainly these, we're assuming smoothness here, so that's certainly sufficient. So that leads us to the equality like this. Right, so these two guys are equal, so therefore we obtain this wonderful identity, that I have apparently lost the ability to express. So the shape operator acting on xu dot xv is equal to what? Well, the shape operator acting on xv dot xu, right? And since, excuse me, but if we look at xu and xv at a point, this forms a basis for TPM, right? Hence the matrix, well, hence S. So P, which goes from TPM to TPM, has SP of V dot W equal to V dot SP of W for all V and W in the tangent space, which means that this is so-called symmetry. So the S of P is symmetric linear operator, or transformation if you like. And that then implies that the matrix of SP with respect to any choice of basis is symmetric in the usual sense of matrix linear algebra. Now, I'm not going to go through all of the details to get from there to there, or even to get from here to here, but I'll leave some of those to you, okay? Sufficient to say then that we have shown that the shape operator is a symmetric linear operator on a two-dimensional tangent space, and that is very nice to know. So SP is symmetric. All right. So what? Well, uh-oh, my book has fallen apart. Oh no. I mean, part of the reason for that is I took it apart, but, let's see here. Now, we need that symmetry, really, to prove the theorem. And the theorem basically is this. Theorem is that the matrix of the shape operator is equal to K1, K2, 0, 0, with respect to a principal basis, let's say. Now, I guess that's a little bit ambiguous in the umbilic case. So for P non-umbilic, that's easy enough. The basis is just E1, E2, where K of E1 is equal to E1 times K1, oops, and K of E2 is equal to K2 E2, with K1 the maximum of the two curvatures, all right? And then for P umbilic, we just we have k of, I mean, if it's umbilic, you can choose any basis. It doesn't, I mean, anyway. Well, for p umbilic, any orthonormal basis will do. The details of the theorem will become clear as we do the following calculation. Where was I? Page 10, I believe, yes. All right, so so the proof, I suppose there's always a maximum, right? It's just that in the umbilic case, the maximum is the minimum. Yeah. So proof, let's say K1 is equal to K of E1, right? And we know that K of E1 is S of E1 dot E1 by definition of the normal curvature. And so choose E2, and this is all in at a particular point P in the tangent space to M, right? So choose E2 in the tangent space to P at M with E2 dot E1 equal to 0. Okay, we can do that. And so then we have a basis. E1, E2 is orthonormal basis not 2, but for TPM, right? So if U is a tangent vector to P at M with length 1, then it follows that we can write, well, it's always true that we can write U is equal to like U dot E1 E1 plus U dot E2 E2, right? But if U is also length 1, that means that this squared plus that squared is also 1, which means you can identify these, of course, as cosine and sine of some angle. So we just let theta be, you know, real number such that what? Such that U is equal to cosine theta E1 plus sine theta E2, all right? And in view of this angle, right, we can study k of theta. So to each u, each u is associated to a theta, so it brings us, I'm going to call it g, just to give a different name. So g of theta will be k of, k of u, but keep in mind that that's really what? That's s of what? Of cosine theta E1 plus sine theta E2 dot cosine theta E1 plus sine theta E2. All right. Now, to be more specific about all this, we should let the matrix of the shape operator, and of course this is the shape operator at P, just to be clear. The shape operator of P, then we can denote it by A, B, B, C. The reason I can put B in both places is because we just proved that the shape operator is symmetric, right? Now you say, well, you proved that for the partial velocity basis, you didn't prove it for this basis. That's true. That's true. So there's a gap in my argument, isn't there? Maybe you can fill it. Now, let's see here. This means like this is tied to the idea that SP of E1 would be A E1 plus B E2. SP of E2 would be B E1 plus C E2. That's what this matrix is shorthand for. All right. So that being said, g of theta then has the following formula, right? G of theta is actually what? It's cosine theta s of e1, well, it's cosine squared theta s of e1 dot e1 plus cosine theta sine theta s, fine, sp of e1 dot e2, and, well, let's see here. There's two of these two terms because of the symmetry here. So like you can see sp of e1 dot e2 is b, sp of e2 dot e1 is b. So there's just two of those because of the symmetry. And you get sine, cosine, cosine, sine, right? And then we've got plus sine squared theta sp of e2 dot e2. But maybe you can recognize that this is really just A, this is just B, and this, of course, is that constant C. All right. And the point P is not varying, right? This is all happening. We're looking at one tangent space, TP(M), and we're studying how if U changes by sweeping that angle around, how the normal curvature varies as the theta sweeps out the full circle of directions based at that one point on the surface. Now, so just to clarify, we have g of theta is equal to, let's see here, a cosine squared theta plus c sine squared theta plus 2 cosine theta sine theta times b. All right. We'll need that for what follows. So, excuse me, 11. Now, we know that K1, which is equal to K of E1, right, is max normal curvature, right? That's by construction. And also, we have U is equal to cosine theta E1 plus sine theta E2 by construction. So to get E1, we put theta equals to 0, gives us U equals to E1, right? Which gives us that G of 0 is a maximum, right? So that must mean then that G prime of 0, if it exists, and it does, because theta appears smoothly here, that must mean that G prime of 0 is 0. It's got to be a critical point for G. So G prime of theta is equal to what? Well, just go back to our formula for G of theta, differentiate it, right? And so that's going to give me 2a minus sine theta cosine theta plus 2c sine theta cosine theta plus 2, and then this differentiates to cosine squared theta minus sine squared theta all times b, right? And then, so G prime of 0 equals to 0, that actually gives me a condition on a, b, and c. Well, what does it actually give us a condition on? Sine of 0 is 0, so that goes away, that goes away, that goes away, but what's left is 2b. Aha! So therefore b has to be 0 by our construction. And while we're at it, what's G prime prime? G prime prime, G prime prime of theta, well, to start with theta, is what? And I don't really care about this term anymore, I just learned that that's 0, right? So what we have is 2 times, well, fine, 2 times c minus a, and then the derivative with respect to theta, right, of sine theta cosine theta. And so what's that? That's 2 times c minus a, and that gives me cosine squared theta minus sine squared theta again. Funny. Now, g of 0 is maximum. Tells me that g prime prime of 0 has to be less than 0 by the second derivative test. But if we put theta equal to 0 into this quantity, of course sine drops out. So what I get is that 2 times c minus a has to be less than 0, which is to say that c minus a is less than 0, which is to say that c is less than a, which is to say that a is greater than c. All right. So, although I suppose to be fair, I didn't say it was a non-umbilic point, so I didn't assume that there has to be, that the curvature has to be non-constant. So it could be that this is equals, because if the curvature is constant, you could get equality here, I think. And so I really should allow for that. And that way I've included the umbilic case in this analysis. Now, okay, so we figured out b was equal to 0. And so what do we have then? Thus, the matrix for the shape operator is equal to what? It's equal to a 0, 0, c, right? With a greater than or equal to c. And so what that means then, converting back to the world of equations rather than matrices, that means that SP of E1 is equal to AE1, and SP of E2 is equal to CE2. All right? Which goes to show you, of course, what? We started by just taking E2 to be an orthonormal vector to E1, but as you can see, it's, what is it? It's an eigenvector, isn't it? It's an eigenvector with eigenvalues, C. And so thus, let's see here, identify A is equal to the principal curvature, and C is also equal to the second principal curvature. And as you can see, if there is if the curvature is not constant, right, that means there has to be a minimum and a maximum, and so the equality can't be attained here. It has to be the unequal case, in which case A has to be bigger than C. And so that goes to show you in the non-umbilic case, E2 here has to give you a principal vector which gives you a curvature less than curvature 1. Sorry. Let me collect our thoughts together here. All right, so that's pretty much it, I think. Now, that gives us a corollary. If there's something I've missed here, you can look at page 214 in O'Neill. In particular, the last equations 3 and 4 in his proof, there may be something in there that I'm glossing over here at the moment. It's getting hot in the garage again. As the temperature goes up, my reasoning goes down. Anyway, here K of U is equal to K1 cosine squared theta plus K2 sine squared theta. That can be, that's I think he calls this Euler's formula for normal curvature. That Euler, what didn't he do? So you can just about see that. If you go back and plug in our u as a function of theta and work it out. This will pop out from the calculation we just did. Alright. So with that almost complete proof of this theorem, I'm going to stop the tape before I do something stupid. I'll start again in a minute.